Hello everyone and welcome back to the fourth session of week 11 of NPTEL course in pharmacognosy and phytochemistry. So far we have learned many methods of evaluation of herbal drugs, of which in this week particularly we are focusing on the chemical methods of analysis. So when we saw chemical method of analysis, we divided it into two parts: the quantitative methods, which included the phytochemical test, identification test, microchemical test, histochemical test. We also saw tests for heavy metals as well as thin layer chromatography to identify the compounds present in your herbs. Now, in this week what we are dwelling more are, we are seeing different quantitative methods, and if you recollect, in quantitative methods we have already seen HPTLC as a method of analysis. Also we have dwelled into HPLC method of analysis. In today's session we will be studying into a little detail of how gas chromatographic techniques can be used. So previously in the HPLC method we also saw that HPLC could be used for determination of pesticides, it could be used for determination of aflatoxins. Not only that, it could be used for quantification of majority of your phytochemicals. Now in today's session we will see the gas chromatographic method. So what is this gas chromatographic method? So gas chromatographic method, as the name indicates, uses gas as a mobile phase, and the chromatographic separation is carried on a stationary phase which might be a liquid or which might be a solid. So this stationary phase, if it is solid, it is referred to as gas solid chromatography, and if this stationary phase is a liquid, in that case it is referred to as gas liquid chromatography. So why do we use gas here? So basically gas chromatography is a technique where your substances, especially when you take the samples from the plants, these samples have a low boiling point, or when you heat it they do not deteriorate. So they are thermally very stable compounds which do not decompose on heating, and they have varied low range boiling points. So the changes in their boiling point, their affinity to the stationary phase can be used and can be modified by using different combination of gases as well as stationary phases. So you can change the mobile phase, you can change the stationary phase and cause a good separation. Now this separation can be better in some cases, especially for volatile compounds, as compared to HPLC. In such cases your gas chromatography is used. So what is this gas chromatography? So initially what we will do is, we have a sample here. Now this sample could be a plant, say for example a plant containing volatile oil. Take for example your eucalyptus. Okay. So now your eucalyptus oil is to be extracted, and I want to see what all volatiles are present in your eucalyptus. So if you take this eucalyptus, I will extract it in a solvent in which my volatiles are more soluble. So in your HPLC, where I wanted other compounds which were non-volatile, in this case, since my intention is to analyze the volatiles present in my eucalyptus leaf, I will choose a non-polar solvent, because most of the volatile oils or volatile ingredients are lipophilic in nature. So I may take a solvent like your chloroform or your hexane or a dichloromethane to dissolve and extract the solvent. This solvent, once extracted, will be injected here. You can see here, this is kind of an injection point, and in this injection point what is happening is, you also see a gas cylinder here. So from this gas cylinder, like I said, this is your mobile phase for your gas chromatography. So a inert gas kind of moves through this column. So what is column, we'll discuss it shortly, but right now just imagine it something to we imagined earlier, like your HPLC column where your compounds are going to resolve. So from this column your gas is moving, your eucalyptus is injected, and at the same time it is being heated. Now what is going to happen is, every component of eucalyptus, say for example your eucalyptol or pugilone or your menthol, all of them have a slightly different boiling point. So they will kind of volatilize, and depending upon their boiling point they will evaporate and come into vapor phase. Once they come into vapor phase, they will start moving along with the carrier gas. As they are moving in the carrier gas, they further get resolved into this column based on their affinity either to the stationary phase or to the mobile phase, and then they are eluted. Once they are eluted, they are detected by the detector, and this is how you see the chromatograph. So you can see from this eucalyptus leaf, I could nicely separate compounds such as sabinine, eucalyptol, menthone, levomenthone, pugilone, so many things. Okay. So all of these volatiles are then separated based on their boiling point, based on their affinity. So usually the low boiling compounds come out first, whereas the high boiling, less volatile compounds come out in the end for a gas chromatography. Now similar to HPLC, what you can do is you can analyze this peaks for area under curve. So if you have a standard concentration being injected and you can prepare a standard curve, based on that you can then put an unknown concentration, just kind of extrapolate it on the graph, and you can determine how much eucalyptol is present in my eucalyptus sample. So I can do the qualitative analysis, what all compounds are present, is eucalyptol present or not, as well as I can do the quantitative analysis by injecting or analyzing it with a standard concentration of eucalyptol. So how do we go about this? So step by step, the first and the most important step for gas chromatographic analysis is sample preparation. The sample is very vital here because the requisites for the sample is the sample should be low boiling or volatile, and the second requisite is it should be thermostable. The reason is, in your gas chromatography we are going on steadily increasing the temperature, and that is where you say your compounds start evaporating based on their boiling point. So you have to convert your compounds into what are called as volatile derivatives. So this sample preparation for volatile oils is not at all a problem because the compounds as such are volatile. But imagine there are compounds which are not volatile. So is it that my gas chromatographic techniques cannot analyze them? They somehow can be analyzed if I can kind of derivatize them. So first thing what I have to do is I have to see how much amount of volatile compounds are present in the sample. If need be, concentrate the extract to get a good fraction of it. Now once I concentrate, I should take into consideration what is my analyte. Is it a volatile compound or is it a non-volatile compound? Say for example, when I was talking about terpenes, eucalyptol, menthol, they are volatiles. I need not do any derivatization of them. But take for example your fatty acids, your lipids, your cooking oils. Your cooking oils are not low boiling, they are not volatile. In that case, you have to modify them to make it more volatile, and only then they can be analyzed. The good part of it, both of this are thermally stable. So there are some derivatization techniques which are often used. One thing what is used is silylation. So you convert your compounds into what are called as trimethyl silyl derivatives. So say for example your fatty acid is RCOOH. So I can convert it into a RCOO silyl, and to this silyl I can have trimethyl. Now you will see that comparatively, now when it is converted into esters, this can even happen with alcohol. I can convert ROH into trimethyl derivatives and so on. So first thing what you can do is silylation. Converting it into silyl derivatives will definitely make it more volatile. Another approach is if you have an alcohol, you can do an acetylation. Now this acetylation can be done with the help of compounds such as pentafluoropropyl anhydride or pentafluoropropyl alcohol. Now that will add an group to it, that is your pentafluoropropyl group to it, and that will make your compounds more and more volatile. Similarly, you can also do an alkylation. It could be a simple alkylation using dimethyl formamide, or you could alkylate using boron trifluoride. So this boron trifluoride in presence of alcohol, say for example methanol, will convert it into a methyl ester. So you can use methanol, you can use your propanol, you can use your butanol in presence of any acid, or BF3 will convert it into a corresponding alkyl derivative. You can also use your tetrabutyl ammonium hydroxide. That is also one reagent which is an alkylating agent. Now in some cases where your compounds are enantiomeric and still you wish to separate it, there are specific derivatizing agents which can cause or help you in chiral separations. This includes your Mosher's reagent as well as N-trifluoropropyl chloride. So these are few derivatizing agents. So you can take your sample, allow it to react with this derivatizing agent. Once this reaction goes forward, you will get these compounds there. Kind of prep up this reaction, get your sample, and this sample you analyze by your GC, you will have much better results because now your compounds are more volatile, and some of these derivatizing techniques also convert your compounds into more stable derivatives. Now not going deep into this, but there are different columns which can be used in gas chromatography. Sometimes these columns can be entirely packed column. So you know it's like a circle or a hollow column which is good or big in length, and this is completely filled with a porous solid. That porous solid will allow the gas to pass through, but because it is completely filled, this is called as a packed column. But sometimes you have what is called as tubular column. So what it is you have a tubular structure in there. So in this tubular structure, certain times what happens is your stationary phase is coated on this. So this is what is called as wall coated column. In some cases you might have certain support like a porous silica. So this is called as support, and this support can be coated with your analyte. So imagine this support beads. Now they are coated with one more layer of your stationary phase. This is what is called as support coated. Then you have your multicapillary, then you have your microchip. Multicapillary is something you can imagine. You have a whole column which is filled by numerous tiny capillaries, and inside each capillary is your stationary phase, and from that your gas is moving. So this increases your rate of mass transfer and increases your rate of efficiency. Whereas if you go to see the microchip one, microchip can be in a varied form. So you can imagine, you know, it's kind of fabricated, and imagine now inside this, through this your gas is passing. So again you have a good amount of area. Now this could be circular, trapezium, quadrangular, or any shape depending upon how convenient it is to fabricate it. Not only that, you can play with temperatures for analysis of different compounds. Say for example your volatile compounds. Your volatile compounds are generally heated between 150 to 300 degrees Celsius for their analysis. If you want to analyze steroids, they are derivatized, and post derivatization they are heated to about 250 degrees Celsius. Pesticides are very resilient. You require little higher temperatures with it. So for pesticidal, many of the methods even go to a temperature as high as 400 degrees Celsius. Now here the different carrier gases are also important. The most efficient ones are your hydrogen and helium, but the problem with hydrogen is combustibility, so we prefer helium over it for its inertness. The other gas is nitrogen, but nitrogen slightly decreases the efficiency. Still you can use air also if you want a little cheaper substitute, and in some cases it is also blended with oxygen. Now once the compound is separated, it goes to the detector unit. There are different types of detectors which are used in the GC. So the different type of detectors which are used in analysis of your gas chromatography is thermal conductivity. Here what is done is your thermal conductivity of your helium gas, which is normally passing through, is measured, and when your analyte comes out, what is happening, the thermal conductivity is changing. So that change in thermal conductivity will give you a signal. Same way, normal helium, you check how much that gas can ionize your, say for example, mobile phase. Now compare it with your analyte moving through that column. The degree of ionization changes when you have a compound coming out. How much is that change? That is detected by a peak. Same way you can see the intensity. Certain times, certain metals produce light of a different intensity. So that is where you measure your light intensity. So in a similar manner, you can see the flame color change in intensity and analyze it, and that is what is called as flame photometric determination. Apart from that, you also have electron capture detector, where you have kind of a small radioactive element or a mechanism where electrons are completely bombarded on a detector surface, and whenever your analyte passes through it, what is going to happen is there is going to be some change in the electron flow. That change is kind of perceived as a signal. Sometimes some compounds are made to glow, we call it as chemiluminescence. This is used for detection of sulfur as well as nitrogenous compound. So of our importance, let us see few examples here. So this is an example of analysis of a volatile oil, and you can see here that during the volatile oil, especially this oil is your peppermint essential oil, pudine ka tel. So when you are analyzing peppermint essential oil, we want to separate out the different compounds in it. So essential oil is just not 1-2 compounds, it might contain somewhere between 20 to even 100 compounds depending upon that, and in some cases they are blended. So take for example, in this gas chromatographic method, they have used a phenyl based SLB column, which is containing almost 5% phenyl substitution. The length of this column, the GC column length, is generally more because the transfer and the separation to take place in gas liquid phase or in gas solid phase takes time. So you kind of buy in more time and more separation by increasing the column length. And this is the internal diameter, that is just 0.25 mm. And if you see that inner coating we just discussed, this is the support and your stationary phase is kind of coated. The thickness of this coating is just 0.25 micrometer. Now what you are going to do is you are going to inject the sample. In some cases where the analyte is very low, they use what is called as split-less injections, but when the analyte is in high concentration, you can also define a split ratio. So your sample is going to get divided and then it is going to get analyzed. So after splitting, mostly for volatile oil, splitting is desired. So after splitting, you start hitting a temperature of 200 degrees Celsius. So that's your injection temperature, and there most of your compounds will volatilize. Now if you see your column oven, your column is located inside the oven and your starting temperature is 50 degrees Celsius. So all your compounds will start getting heated and mobilizing from this point, and it is continuously being heated at the rate of 3 degrees Celsius per minute. So after 1 minute it will be 53, the second minute it will be 56. This goes on till you reach a temperature of 300 degrees Celsius. And if you see the detector temperature is set at the highest point, that is 300 degrees Celsius, with a carrier gas, that's helium, with a flow rate of 30 centimeter per second. So when you kind of put this whole thing in a program, you will get a kind of chromatograph which looks like this. And then if you subject it to a mass spectroscopy, this mass spectroscopy many a times is coupled with library search. This includes your NIST, what is called as the NIST library. You have different in your LCMS you have the Melton's library. Now you have your MZMind library. There are many multiple libraries available. Now with machine learnings, they even have a fragmentation based plant metabolomic library. So even you can use that, you can use something like your softwares to analyze this, and based on those fragmentation patterns, based on those retention time, your output, your computer will tell you, you know what, these are all the compounds. So at number 1 you have diethyl tetrahydrofuran, the peak what you are seeing as number 2 is thujine, and so on. So not only will it tell you which peak is what, it will also tell you the relative concentration based on the area under curve. So this is one which can be used for quantification of essential oils. You can also quantify total amount of lipids, fats, sterols by either alkylation or acetylation. And similarly, when you see, if you remember your HPLC, we did what is called as pesticidal residue analysis. Now this is very vital, and it is also, or it can be also analyzed using gas chromatography. So we use the very same Quecher's method, and here what you are going to do is the same sample extraction. If you recollect, in the Quecher's method, it was your sample which was pulverized, then acetonitrile was added, then water was added, and slowly you added salt like your magnesium sulfate. What happens is, the more salt you add, the acetonitrile is pushed out. This acetonitrile was taken, passed through more of what is called as solid phase extractors, cleaned up, centrifuged and analyzed. Now this analysis again can be done on a very hydrophobic GC columns such as your HP columns, and in this case you can observe different pesticidal residues being there. Now this method has also been notified by AOAC. Here what they do is they kind of use a very standardized methods. So this standardized methods of GC are also there in terms of how you should prepare your sample for GC analysis of pesticides and what program should be set. The good part of this is nowadays most of the equipments, especially if you go to see makes such as Agilent or Shimadzu, these companies already have a preset softwares for pesticide. So if you already have a program which is there in your machine, you just run your sample. Not only will they analyze your sample, the programs are so accurately set that based on their retention time, they can tell you which pesticide is there and at what concentration. So in their softwares, data of 300 to 400 such pesticides are already locked. So the moment you analyze it using their methods, you can see that the machine will tell you that this many pesticides with this many quantity are present. Now the next part of our analysis is solvent analysis. Now many times what happens is, when you are preparing herbal extracts, we often use a solvent. So this herbal extracts, you can extract it in alcohol, chloroform, pet ether, so on. Now sometimes the solvents are very inert, but many a times the solvent are undesired and we do not want them in our preparations or medicines, and as a result there is always a limit to solvent given in every extract. So how do you do the solvent analysis? Now solvent analysis can be much accurately done by what is called as headspace analysis. So now what is this headspace analysis? Take for example, this is my sample. Now this is where your extract is. Okay. So I put my extract here and my extract is kind of very viscous. It cannot be volatilized. Imagine a consistency like your Chyawanprash. So it's non-volatile. It's definitely going to, clog my machine, my syringes, whichever I'm going to use. And as a result, it's not recommended that I inject this extract in the machine. So what is done is this extract or sample are carefully heated in the vial, and this vial are nicely sealed. So when I'm heating this gradually, what is happening is, as the temperature increases, it reaches to this boiling point of the solvent. So methanol, you can say at about 60 or 70 degrees Celsius will start boiling. You will have chloroform. These are all low boiling. So if my temperature is crossing 100 degrees Celsius for this sample, most of my solvents will start volatilizing. Then what I do is I incubate it at a particular temperature, and this incubation will help in equilibration. So I will not say my entire solvent goes out in the headspace, but what I say is my molecules of solvent equilibrate between air as well as the sample phase. So once this equilibration is achieved, depending upon their partition coefficient, I will know how much is going to be there in my extract and how much is going to be there in that. So the formula for that is aptly there. Now what is going to do is your headspace analyzer will come in, it will prick the needle in this vial, it will kind of take in all the headspace. So it will kind of use vacuum to pull in all these vapors which are generated, and this vacuum will now take in your ethanol, methanol, chloroform, whatever is there. Now because of this, now everything that is there in headspace is now pulled out, and that volume is injected into your gas chromatography. So what will happen, depending upon your boiling point, you can see different solvents that are all present will be seen. So whether it's alcohol, whether it's even toluene or chlorobenzene, whatever has gone into that extract can be analyzed using my solvent residual analysis by headspace capturing. So in some cases they also use what are called as adsorbents. So in that case what is happening, this is used in the perfumery industry. So there is a probe here, and what does the probe do is, when you spray perfume, there is what is called as top note, which is made up of more volatile compounds. But after an hour or so, the volatile compounds vanish and you get what is called as the middle note and later on the base note. To see what changes happen, they kind of put that perfume or spray that perfume in this, okay. Then what you will see is the first note is being captured by this adsorbent, and this adsorbent phase is then used for gas chromatography. So it will analyze the first note. After 1 hour again a next probe of adsorbent is pulled in. So it's just kind of a modification of headspace, where instead of vacuum the whole thing is kind of adsorbed for a certain period of time and then analyzed. So definitely you could use GC for compounds which are more volatile, like your pesticides, like your solvents, like your volatile compounds, and you could use for non-volatile compounds which can be converted into volatile derivatives and are thermostable. But all in all, if you see in terms of versatility over HPLC and GC, your HPLC methods are still preferred. So this headspace analysis is going to use or going to give you a more versatile or more user friendly approach even with the sticky residual samples, and it's not necessary here that the sample should be volatile. So the temperature oven can help you regulate whatever volatiles are present, and this can be done even on a ml scale. So there might be vials which are as small as 2 ml, there might be vials which are big as like 100 ml for headspace analysis. This is all sucked in and put into your GC, and that can help you analyze the solvent. So here are few references if you wish to read more about the gas chromatographic analysis, and thank you everyone for your patient listening.